Well, thank you for coming today. I appreciate the opportunity to tell you about Afx beam control technology. Today's talk will be in two parts. I'll first give you an introduction to Afx, tell you about the motivation for developing it, some of the underlying technology, and discuss the beam characteristics that are important for additive manufacturing. I'll also give briefly a few application examples, though I won't go into that in great detail because there are several talks at FormNext on that topic from various partners. In the second part of the talk, Chris Luetjen, who's the system engineer for these products, will talk to you about the features and advantages of Afx and nLIGHT fiber lasers in general that facilitate integration into tools, including the user interfaces and communication protocols. So, in a sentence, what is Afx? It's an industrial fiber laser with rapidly tunable beam profile that's been optimized for additive manufacturing. So the beam can be adjusted from a standard single mode 14 micron beam here to a 40 micron ring shaped beam and all shapes in between. The motivation for developing such a technology actually goes beyond additive manufacturing. In general, it's been known for decades that materials processing performance depends on the laser beam characteristics, the beam's size, shape, and divergence. To take two examples from more established or legacy applications, in sheet metal cutting, it's known that fiber lasers have really taken over for thin metal and nitrogen cutting, but for thick metal, oxygen cutting, particularly mild steel, they were not able to achieve the edge quality of CO2 lasers. Here's a 25 millimeter mild steel sample cut with a standard fiber laser from 100 micron fiber, and you can see the poor edge quality. It's been shown that by going to a larger 300 micron ring-shaped beam, one can get much better edge quality, in fact rivaling a CO2 laser, which has allowed fiber lasers to then displace CO2 lasers in this last important application, but they couldn't do so before they had this beam shaping capability. Similarly, in welding, it's known that a small beam gives you a deep penetration keyhole weld, whereas a larger beam will give you a more shallow conduction weld, which could be desirable for aesthetic or quality reasons. What's going on here, of course, is that the material processing performance depends on how the heat is deposited into the sample, and that in turn is affected by the beam characteristics. And so to precisely control the heat deposition is necessary for controlling the feature size, for maximizing the production rate, for maximizing part quality, and also for versatility for different materials and thicknesses as shown here. But what about additive manufacturing? Well, the need for spatial control of the beam is really clear here. In typical additive parts, you have both fine detail and larger scale features. In order to be able to print the small scale fine features, most laser powder bed fusion tools use single mode lasers, which give you a diffraction limited beam, which gives you the smallest size so that you can write these small features. However, when you go to write the larger features, the small beam doesn't work for you in terms of high productivity. The analogy would be if you had to paint a painting and only had a fine point paintbrush. To make these larger features, you'd like to increase the spot size and thus be able to increase the deposition rate. And in the general case, you need a laser that can go between the small single mode spot size and the larger spot size to maximize the productivity on the part. What about beam shape? That's about beam size. So a single mode beam has what's known as a Gaussian beam shape. It gives you diffraction limited propagation, and that's important for having the smallest spot size, the longest working distance, and the largest depth of field, or the largest process window. And so it's essential not to give up that shape for making your fine features. However, for the larger features, it's not clear that that's the best shape. In fact, it's probably not, because this peaky shape leads to highly non-uniform heating. If you have a certain melt threshold for the material, much of the beam is below the melt threshold, and the peak tends to be above the melt threshold. And that gives you excessive heating, which can increase the vapor pressure and lead to deleterious effects like spatter, soot, and porosity. Current tools will attempt to address the problem of size by working off focus. That is, moving the workpiece away from the focal plane. That makes the beam bigger, but it reduces your process window because now the spot size is changing drastically with position, and so you get a very small process window. Also, this doesn't address the non-optimized Gaussian beam shape. The larger beam still has the Gaussian shape and thus still has the excess heating problem. So what's found is you can simply just turn up the power, make the beam bigger, and go faster. You do get inadequate material quality. So thinking about what would be a better shape, you have to think about the temperature profile that is in the material. A Gaussian beam, as shown here, leads to an even peakier temperature profile, typically peakier than a Gaussian. So to try to flatten that profile, you want to make the laser spot larger and flatter, and one might think, oh, I'll go to a flat top laser spot. But actually, even a flat top laser spot doesn't give you a flat top thermal profile because of thermal transfer, conduction in the material. You still get a peaky profile. To get a flat profile, you want to push more intensity from the middle of the beam to the outside towards a ring type of profile, as shown here. Now, it could be just a ring or a ring with some power in the middle. The details of the shape depend on the material itself, the thermal conductivity of the material, the power level, the speed. And so you actually want to be able to adjust the beam shape to get the optimum temperature profile. Maybe getting ahead of ourselves, this effect is actually shown here in laser powder bed fusion of an Inconel 718 part, where you see the peaky temperature profile gives a balling of the material, and you can eliminate that by going to the more ring-shaped profile. Unfortunately, most lasers until now have had fixed beam characteristics, and so you couldn't take advantage of this effect. Various downstream methods have been introduced to tune the beam profile, but they've largely proven impractical. They often involve free space optics, and they increase the cost and complexity and or decrease the performance and reliability of the tool. So although these methods exist, they haven't really been widely adopted. So that's really what motivated us to take a fresh look at the problem and develop a new approach, and that's the Afx Fiber Laser, where we can rapidly tune the beam characteristics directly from the fiber laser, right out of the delivery fiber, as shown here. These are actually CMOS camera images of an actual 1 kilowatt beam, and it's switching between the single mode shape that I showed you to the 40 micron ring out here and shapes in between. The key points of this technology are that there are no free space optics. This is done all in the laser, all in fiber. We have a wide variety of optimized beam shapes and sizes. The Gaussian that I mentioned, also flat tops and ring beams, and they're different versions. This was the single mode version. Here's a multi-mode version where the beam goes between a 100 micron flat top and a 330 micron ring. The switching among these shapes is very fast. It's less than 30 milliseconds, and so that allows you to optimize each step of the process on the fly. The laser does not have to be blanked or turned off during the switching. It can be done in real time, just as you might modulate the temporal characteristics of the laser. You can now change the spatial characteristics. Being an all-fiber technology, it's highly reliable. We've done an accelerated life test where we did 20 million beam changes with no measurable change in performance. This isn't a single laser, a single product. This is actually a very versatile technology platform, as indicated in these two examples, where we can get a wide range of specs with different fiber designs. And because this is an all-fiber technology, the power scaling is only limited by silica fiber, just like a conventional fiber laser. And so we offer in the multi-mode version currently up to 15 kilowatts. In fact, the multi-mode design was introduced 3 years ago, and it's been widely deployed in high-performance cutting tools by leading tool integrators worldwide. And we introduced the single-mode version, Afx, last year at Formnext. And so although this is a relatively new technology for additive manufacturing, it's actually well established and widely deployed in the field. So how does this work? How do we tune the beam all in fiber? There are three basic components. The first is the feeding or the delivery fiber from the laser has multiple guiding regions. And I'll show you the example with the multi-mode case, but the single mode is essentially the same. And so in the multi-mode case, we have the 100 micron core surrounded by a 200 micron ring surrounded by a 300 micron ring. And we can get different beam shapes by partitioning the laser among these different regions. And so varying this partitioning varies the size and shape of the beam. Conceptually, this looks like this. You can imagine, again, just conceptually doing this in free space by focusing the beam into this fiber and sort of physically moving it to move the beam into these different guiding regions. This is not what we do, right? If we did this, it would be no better than any other free space contraption. Instead, we have no free space optics. We bring the laser beam in its fiber, and this is a special fiber that when it's perturbed, it gives this beam shifting effect. And so we're shifting the beam radially in the fiber and then coupling it into these different regions. Now there are several different perturbation approaches we've thought of. This figure is actually from our patent, which shows the effect of gentle bending on a fiber with a particular refractive index profile, and that is one way to do it. This device is then integrated into the fiber laser by splicing it in between the laser cavity itself and the feeding fiber, and so it retains all of the fiber laser performance and reliability benefits. This is still an all-fiber monolithic train. To the end user, it's invisible that this is there, except that it has this magical beam tuning ability. So looking at AFX in particular, we have, as I said, the single mode core, and then a 40 micron ring, and the beam power is being divided up among these, 60% in the core, 50, 40, 20, etc., and the rest of the power in the ring. We call these different settings the index value from 0 to 6. If you look at the calculated beam size, and now beam diameter is not a great description of the beam, right? It doesn't really capture the shape, but there are standard methods to sort of calculate a size. And so the calculated size goes from about 15 to about 45 microns, or in terms of area, this is nearly a 10x dynamic range in the beam area. So a huge range in the irradiance or heat deposition into the workpiece. If you calculate m squared, the standard measure of beam quality, of course the single mode is near m squared equals 1, and the largest beam is m squared of about 5. Now, as I'll show you, even though this m squared is multi-mode, of course, it's a ring beam, it's actually still quite a low m squared, and the beam maintains an excellent depth of field or a large process window, and I'll show you that momentarily. Whoops. The last is that the power currently offered is 1200 watts. We actually turn the power down for the single mode setting to 850 watts when you have a 10 meter fiber, because just like a standard single mode fiber laser, if the feeding fiber gets too long or the power gets too high, you get nonlinear processes in the fiber. So at 10 meters, that's 850 watts. Of course, this would be higher with a shorter fiber or lower with a longer fiber, just like a standard single mode fiber laser. The full 1.2 kilowatts is available in these larger settings. I want to do a brief aside on the beam quality, or m squared, because that's something a lot of people think about in these high precision additive manufacturing tools. M squared is the standard measure to characterize beams, and a perfect Gaussian diffraction limited beam has m squared equals 1, and any other beam has a larger m squared. If you look at a single mode fiber, it doesn't actually give you m squared of equal to 1, because it doesn't actually give you a true Gaussian beam. When you solve Maxwell's equations in the fiber, it doesn't produce a Gaussian. It produces something that's really close to a Gaussian, but not quite. And as a result, m squared is always a bit bigger, typically between 1.05 to 1.2, maybe even as high as 1.3, depending on the fiber design, meaning the refractive index profile, and the measurement method. But much like diameter, m squared does not really uniquely define the beam profile or its propagation characteristics. And so if you want to think about, is this beam quality sort of good enough for my application, you really need to look in much more detail than just this single number. And so we've done that. If we look at the Afx index 0 beam, it's really best described as a sum of a standard single mode fiber beam and a little bit of power in the ring. And so in black is the profile of the beam out of one of our standard single mode fiber lasers, and in red is the profile out of Afx in its single mode index 0 setting. And you see it basically the same, but you have this little bit of power in the ring. This residual power actually affects the calculation of m squared. In fact, the way m squared calculations are done, this is highly weighted in the calculation, and thus instead of calculating out m squared of 1.1, it calculates that in 1.3. But optical measurements, as I'll show you, actually verify that this index 0 beam has the same propagation characteristics as a conventional single mode beam. And more importantly, several groups have shown that the Afx index 0 provides identical performance to other single mode fiber lasers. So the key point is it's really important not to get hung up on the number, especially when you're dealing with these more complex beam shapes, and you really have to look at the propagation characteristics and the performance. So let's look at the propagation characteristics and the performance. Looking then at index 0, you do these measurements by focusing the beam. This has a magnification of 5, which would be fairly typical for an L-PBF tool. So we have about an 80 micron spot size at the workpiece, and it propagates sort of like a normal Gaussian beam. In fact, a standard measure is what's known as the Rayleigh Range, which is the distance over which the beam expands by the square root of 2. You can kind of think of it as your depth of focus or your depth of field. And so in this case, it's about 7.2 millimeters, which is exactly what you'd expect for a single mode beam. If you look at all the other beams, all the other index settings, you see the larger beam as you'd expect, and it propagates pretty similarly. If you then look at the Rayleigh range or the depth of focus for these other beams, even though m squared is going down, the actual Rayleigh length or depth of focus is going up because the beam is getting bigger. So when you were in the Gaussian single mode setting with, say, a magnification of 5, you had a 3.5 millimeter Rayleigh range. When you go up to index 6, you actually have an over 8 millimeter Rayleigh range. So your depth of focus actually went up. You have more process window when you went to this larger beam. This is a real contrast to some other technologies like diffractive optical elements can make a ring-shaped beam, but they only do it at one plane, and if you move a little bit away from that, you lose that beam shape. So this large depth of focus is a critical advantage of this technology. In fact, we will look now at those propagation shapes, so you don't have to just take my word for it. Here's index 0, again, the Gaussian beam. And if you blow up the region around the focus and you look at the beam, it basically always looks like a Gaussian, because that's how Gaussians propagate. They just expand but stay Gaussian. If you now look at the index 6, the ring beam, the one with the highest m squared value, and blow it up, you see near the focus, over quite a large distance, you retain this ring shape. That's the sort of effect I was telling you about. And so we've looked at many of these beams, and the beam shape is maintained over about plus or minus half a Rayleigh range, or for typical magnifications, about plus or minus 3 millimeters. So again, very generous depth of focus. You don't sacrifice that when you use Afx and these larger and shaped beams. So I think you understand now that the sort of value proposition for Afx, that it's been really designed for additive manufacturing, that when you want to make fine details, you use these smaller Gaussian and near Gaussian spots. When you want to do bulk deposition, you use these larger, predominantly ring beams. And of course, anything in between for mixed parts, and you can switch these settings on the fly as you're making the part. One other point is that these often lasers go into scanning tools which need a collimated beam, and so we have a line of what we call the performance collimator that facilitates tool integration. It has diffraction limited optics, so it maintains the excellent beam quality over the full power range for all of the different index settings. And it's been designed for high power and high brightness, so it has near zero focus shift because it's well cooled, and no thermally induced aberrations because of the quality of the optics. We offer it in 7 focal lengths between 50 and 160 millimeters, and with 25 and 50 millimeter apertures depending on the focal length. We can optionally include an aperture in the collimator, and this ensures that the output is compatible with scanners. Scanners have an aperture, and they often, the aperture and the downstream optics are very intolerant of any power outside of the NA of those optics. And so we include a water-cooled aperture in the collimator to ensure that you won't exceed those limits in your scanner or the other optics. Finally, the collimator can be added or changed in the field. The tolerances on the collimator and on the laser connector are such that they're not, paired. You can swap them or add them in the field and maintain all of the key beam specifications. So just a few slides on applications. It's one thing for me to say that they're benefits, it's another to actually see it in real-world applications. And so several tool integrators and research labs have quantified the benefits of Afx. Here's an early example from Econity 3D, who actually gave a talk here earlier. And they looked at titanium alloy, L-PBF, and they saw a dramatic 7.8-fold increase in the build rate while maintaining excellent material quality, greater than 99.5% density. They went from 5.4 cubic centimeters an hour to 42 cubic centimeters an hour. This is really game-changing when you look at the economics of additive manufactured parts. We often get excited if we get a 20 or 30% increase or a factor of 2, right? To get 8x increase in build rate really changes the economics of which parts it's cost-effective for using additive manufacturing. Here's a result from the Technical University of Munich, who also gave a presentation here. They looked at stainless steel, and they were looking at the build rate, the process window, and the part quality. This shows the speed and the power, and the points show where they got good material. And so the Gaussian beam are the small points, and so the process window is sort of indicated in the enclosed area. And you can see that when you go to the donut beam, you can use more power, go faster, and have a larger process window. In fact, when they look at the part quality, they again, much as I showed you earlier for Inconel, they show this really reduction of balling effects when they went to the ring beams. So what you're seeing here is there's not a trade space here where you're trading off, speed or process window or quality. You're getting better build rate, better process window, and better part quality. So there's no real compromise here. Last, this is a screen capture from a talk that Michael Schmidt gave at iCalio. He's from the University of Erlangen at Nuremberg, and he's comparing with high-speed video the melt pool dynamics from a standard Gaussian beam and the ring beam. And you can just see visually how much more stable the melt pool is, which of course leads to the better material quality, fewer pores, and other imperfections. Last, Afx has been widely recognized in the industry. When we introduced it here last year, Amexi chose it as one of the top 5 metal technology highlights. And this year we're a Prism Award finalist and received the Laser Focused World Innovators Gold Award. With that, I'd like to turn it over to Chris Luetjen to talk to you about integration of Afx into machine tools.
Thanks, Dahv. Okay, so as Dahv mentioned, there's going to be a lot of information this week provided about all the benefits of the beam shaping technology provided in Afx. But we also wanted to talk a little bit about the other features that are unique to nLIGHT lasers, not only the Afx, but our entire additive product line. One of those key features is our hardware-based back reflection technology, which allows for uninterrupted processing of highly reflective materials. I have an example here from the Politecnico Milano, where they tried to print this copper part with a competitor's laser, and it constantly tripped off when the laser ran through normal. They replaced the laser with our laser, and they were able to print it with no issues. We also provide industry-leading power stability and tunability, which is very important for additive manufacturing. We have a 1% power stability spec, that is uniquely applied for our full power range. That means a 1 kilowatt laser being run at 5%, 50 watts, is just as stable as it would be at 1 kilowatt. It means that no matter what your process window is or your power level, you'll get the same consistent results. Our lasers are also highly reliable in the long term. So we've leveraged our 20 years of experience manufacturing high performance components, and we've applied that to all of our additive products. And so they're really designed to be used 24/7 in a high utilization environment and last many, many years. We've also applied a lot of scrutiny to the Afx technology itself. As Dahv mentioned, we've done a life test of over 20 million cycles. And for reference, that equates to about 5,000 index changes per day for 10 years. These lasers are really designed to be used in a full production environment, not just as a lab device. One other feature is we have the fastest modulation rate and rise and fall times in the industry. So that means you can modulate your laser at 100 kilohertz with rise and fall times of 5 microseconds. This is particularly useful. You can apply power where you want it, when you want it, and our electronics are also very fast in their communication. So if you have a multi-laser tool, the gate delays from laser to laser are very consistent and will be less than 4 microseconds. You don't have to worry about lasers emitting unsynchronously. Back to the Afx specifically and integrating it into your tools. We've leveraged our existing design extensively, so it's basically a drop-in replacement for any of our standard CFL lasers today. It's a 19-inch rack mount box and is 4U high. It comes with a standard QBH interface. 5 and 10 meter lengths are standard, and it's powered with a single-phase 220 AC input. All of these lasers come standard with connections to be certified to ISO 13849, so you don't have to worry about any safety implications when you're switching to this. And we also include a CDA port for human environments in case the laser is outside of the tool, maybe somewhere where it's not temperature controlled. There are a few differences with controlling the Afx laser, since we did include new features. One of those is the analog voltage control. As Dahv mentioned, some of our lower indexes have a different power limit than the larger ring modes. And so what we've done is we've done one calibration curve and truncated it when you've reached the maximum power. That means you don't need multiple calibrations for different indexes. 5 volts in this case will always give you 600 watts. And if you try and command a power that is above what's allowed, the laser will just provide its maximum power available at that index. In terms of actually controlling the beam shaping, we've tried to keep this as familiar and easy as possible. And so our laser still has 3 main control modes. There's a software API, there's a hardware interface, and there's also a command line interface through a serial port. We typically recommend using the hardware control. It's the fastest and most reliable. It's based on a 4-pin signal that's basically a 4-bit binary number, as well as a start pin that commands the index to change. If additional hardware pins are not available, you can also control the beam profile through the software API. That can be a little bit easier sometimes if the machines don't have extra pins. You're also free to sort of mix and match control modes. You can drive the laser through the hardware and control the beam profile through the API simultaneously. And we're also working on a bit of a more flexible mode that's coming out next year that'll allow some pins to be repurposed so you can really drive the laser in the way you want to. So that's all I have. If anyone has any questions, we'd be happy to answer them.